Hi again. So in the previous lecture, I explained how you read the table, especially those four numbers. So the estimates for beta 0 and beta 1, which is the key essence of the estimate, is presented here. So the intercept is 0.64 and the slope is 2.30. And so using those two numbers estimated results, you can predict the outcome variable GDP growth rate in this example using a specific value of a trade share of the regressor. So for example, suppose that there is a country whose trade share is 60%, 0.6. And then what would be the GDP growth rate for this country? And you can calculate just the prediction. You can just predict using this equation, using this regression equation. But first, drop the error term because you cannot predict error. So drop the error and then use beta 0 and beta 1 estimates in their respective places. And x, the value of x should be given by the question or by an assumption. So your growth, this country's growth, will be the intercept estimate from this number. So this number is taken to the intercept, and plus, and the slope estimated here times the assumed trade share value, so 60%. Then calculate this, simple, calculate, multiply, and add. Then you get 2.024 something. So this country's growth rate is predicted to be about 2% point, 2%. So in the homework, you are going to do something similar to this with a different trade share. So it will be almost automatic. So you can do that easily. Okay, now we learned how to use the coefficients, and then let's go to the top right side of this panel. So first, find these two numbers. 65 is, as you see, 65 is the number of observations. So number of observations, which is usually denoted by n, lowercase or uppercase n, and more academically we call this the sample size. The sample size is 65, and in our data set, you can check that there are 65 countries. So the number of countries in our example is provided here. So, and R squared is 0.1237. So we learned it in the previous lecture. So the R squared, this R squared means about 12.37% of the variation in the GDP growth rate is explained by the regression model with the trade share. So the trade share explains about 12% of the GDP growth rate. That's how we interpret the R square. Then is it good? Or so 12% is not bad. So there are a lot of different factors, many other factors that will determine the GDP growth rate. But using only one variable, you could explain 12%, which is actually more than I expected. I would be satisfied even if it was like 5%. So trade share could explain a lot. And okay, so R squared is, so I'm going to come back to the definition of the R squares in a few slides. And let's think about those things. So SS it stands for sum of squares, and TF stands for degrees of freedom, and MS stands for mean square, which is simply, so this column, mean square column, is calculated in this way: sum of square divided by degrees of freedom. So as you see, the first line, sum of squares is 28 and divided by 1, so mean square is 28 something. So mean square can be calculated directly from those two numbers, sum of squares and degree of freedom. And there are 3 different types of sum of squares, which were already defined in a previous lecture too. So let's see them. But the problem here is, as I mentioned at that time in that lecture, in the previous lecture, that the definition or the term may differ across programs and textbooks. So different people call them different way. So let me explain what is what in this lecture. So the first line says model. So the Stata program calls something model sum of squares, but that was not the name used by the textbook. Our textbook uses explain sum of squares, abbreviated to ESS. So explain sum of squares is defined in this way. So you predict y using y hat and calculate y hat, the variation in y hat, by subtracting its mean and squaring them and sum all the squares. So this is explain sum of squares, which means how much you could explain using your predictor. That's also ESS was the name used by the textbook, our textbook, but Stata uses a model sum of squares. They are basically the same thing. And degrees of freedom in this case is 1. So degrees of freedom for the model sum of squares or explain sum of squares is the number of regressors. But we do not count the intercept. So number of regressors in our model is 1. There is only one regressor, trade share. So the degrees of freedom for the explain sum of squares is 1. It is a little bit not straightforward, or you may understand this as the difference between the other two. So okay, just take it, and the mean square is automatic, so just their ratio. And the second row is about residual sum of squares, which is consistent with the name used in our textbook, which is good. By the way, so I gave you the names model sum of squares and explain sum of squares, but in some textbooks or some other programs, it is also called as the regression sum of squares. So regression sum of squares is confusing because abbreviation is also RSS. Regression sum of squares is abbreviated to RSS or SSR, which is the same as what we use here. So it's very confusing, but names are not important, even though you should understand what they mean, but the same thing can be called differently by different places. So anyhow, so residual sum of squares is defined in this way, which is based on the residual. U hat is the difference between your predictor and the actual value, and see how much variation is contained in is given by the residuals, how much residual varies. If it equals to 0, that means there is no residual. So the smaller the residual sum of squares is, the better your estimation is. So this captures the portion of the amount of variations in your data which is not explained by the regression model. And the degrees of freedom for the residual sum of squares is the sample size minus the number of parameters you have estimated. So in this case, the number of parameters includes the intercept and the slope. So you need to estimate two parameters. So in doing so, in estimating them, you consumed 2 degrees of freedom. So you lose 2 degrees of freedom. So as a result, you only have, so you started from 65 observations, but you lost 2 degrees of freedom. And as a result, you only have 63 for the residual sum of squares, right? So that's how you can read those numbers. And the mean square is the residual sum of squares divided by its degree of freedom. So it's a average, some kind of mean, some kind of average. It follows directly. And then also connected to them is root MSE, which is root mean squared errors. Root mean squared error is 1.79, is given as 1.79, and you can think it as oops, there is a typo. What I meant here is, so what comes here is this mean squares. So mean squared residuals is 3.203 something. So if you take root, then that becomes the root mean squared errors. So the root mean squared error is calculated. So you just take root of this number, which is again the root of residual sum of squares divided by its degrees of freedom. By the way, so root mean squared error is defined in this way, but the problem here is its definition is also different from our textbook. In our textbook, they use the same formula for the standard error of the regression. So standard error of the regression is this thing, RSS, square root of RSS divided by degrees of freedom, exactly what we calculated here. And this means the meaning of the standard error of the regression is the standard deviation of the error term. The estimated standard deviation of the error term is this guy, which means it is the noise inside in the original model in the data. So the noise, the standard deviation of error term, is the noise that you cannot handle. So it's like no matter how many sample you have, you still have the errors, the same amount of error in the error term. So that is this thing. So the larger the standard error of the regression is, the less accurate your estimators will be. So this standard error will affect these standard errors. So in the calculation of these two standard errors, those two standard errors utilize this number. The formula is a little more complicated, so I'm not going to show you the formula, but so then you can see the flow. The residual sum of squares is calculated, and it is divided by the degrees of freedom, which is the mean square. Mean squared error is taken, the radical of the mean squared error is given here, which is also can be interpreted as the standard error of the regression, which is the standard deviation of this guy, which also affects the standard error of each parameter estimate. So it's all the numbers in the table are interconnected. And going back to what I mentioned earlier, when we compare with the definition in our textbook, our textbook defines root mean squared error in this way. The denominator is the sample size n, not the degrees of freedom. So here the denominator was 63, which is the degrees of freedom, but in the textbook it uses 65 as the denominator. So it makes a little difference, but not much. So so you may, as you can see, the same thing is called in different ways. So then in the end, roughly speaking, you may treat those two things equivalently. You may think the standard error of the regression equals or is interchangeable with root mean squared error. I think that's not that wrong. So that is an easy way to understand. And also another way to justify that is that if the sample size n is large, then the difference between those two will be ignorable. So the difference between 63 and 65 is is still small, but when you think about difference between 65,000 and 65,002, that difference will be much smaller. So in the end, those two things will be pretty much the same. Okay, in this video we studied what those numbers mean and what some of those numbers mean. And I am going to resume the same interpretation in the next video. Thanks, bye.